Khaled Ghali, a student of University of Michigan Dearborn. This is a presentation summarizes the Federated Learning paper, Strategies for Improving Communication Efficiency. Um, this is one of the projects that we have to do for ECE 5831, Pattern Recognition and Neural Networks. Let's start. So this is the title of the paper and the writers. I'll be putting the link of the paper below in the comments. Federated learning, the abstract. It is a machine learning setting where the goal is to train a high quality, centralized model while training data remains distributed over a large number of clients, each with unreliable and relatively slow network connections. Now, each client independently computes an update to the current model based on its local data and communicates this update to a central server where the client-side updates are aggregated to compute a new global model. The typical clients in this setting um, are mobile phones, and communication efficiency is of the utmost importance. In this paper, the writers propose two ways to reduce the uplink communication costs. Structured updates, where they directly learn and update from a restricted space parameterized using a smaller number of variables, either low rank or random mask. The sketched updates, where they learn a full model update and then compress it using a combination of quantization, random rotations, and subsampling before sending it to the server. Experiments on both convolutional and recurrent networks show that the proposed methods can reduce the communication cost by two orders of magnitude. Federated learning and related um, decentralized approaches have been proposed as an alternative setting for the existing machine learning algorithms, which have been designed for highly controlled environments such as data centers, where the data is distributed among machines in a balanced fashion. A shared global model is trained under the coordination of a central server from a federation of participating devices. The participating devices, the clients, in other words, are typically large in numbers and have slow or unstable internet connection. So basically, we have a server that can do a certain process, or it can do, but it needs a lot of power to do it, and it needs a lot of data to come from a lot of clients. So what federated learning is that you take the data from the clients and you send it to the server, and then the server is going to be doing the um, processing for all of their data and present the results afterwards. Now, this paper is going to summarize or approach another way um, to make it easier for the server and for the clients as well to send that data, because when you want to send a lot of data to the server, that's costly because you're uploading information on the web, um, and the communication, the network is not isn't always good. So we're going to study how to make it better. For simplicity, consider synchronized algorithms for federated learning, where a typical round consists of the following steps. A subset of existing clients is selected, each of which downloads the current model. Each client in the subset computes an updated model based on their local data. The model updates are sent from the selected clients to the server. The server aggregates these models, typically by averaging, to construct an improved global model. A naive implementation of the above framework requires that each client sends a full model update back to the server in each round. For large models, this step is likely to be the bottleneck of federated learning due to multiple factors. One factor is the asymmetric property of internet connection speeds. Additionally, existing model compressions schemes can reduce the bandwidth necessary to download the current model, and cryptographic protocols put in place to ensure no individual client's update can be inspected before averaging with hundreds or thousands of other updates further increase the amount of bits that need to be up- uploaded. Reducing uplink communication cost is very important for this case, and the writers study two general approaches: structured updates, where they directly learn an update from a restricted space that can be parameterized using a smaller number of variables; sketched updates, uh, where they learn a full model update, then compress it before sending it to the server. So we have either structured updates or sketched updates in this paper that we are going to study. The goal of federated learning is to learn a model with parameters embodied in a real matrix W that belongs to R, which is two dimensions, from data stored across many clients. First, provide a communication naive version of the federated learning in around t, which is greater or equals to 0. The server distributes the current model wt to a subset st of nt clients. These clients independently update the model based on their local data. Let the updated local models be W1T, W2T, etc. until WNTT. So the update of client I can be written as HIT equals WIT minus WT for I belongs to ST. These updates could be a single gradient computed on the client, but typically will be the result of more complex calculations. For example, multiple steps of stochastic gradient descent (SGD) taken on the client's local dataset. In any case, each selected client then sends its select clients. Oh, I have some mistakes here. Select clients then sends updated back the update back to the server, where the global update is computed by aggregating all the client-side updates. We'll be using these equations. The server chooses the learning rate mu t, but for simplicity we choose mu t equals to 1. Note that the parameters of a fully connected layer are naturally represented as 2D matrices. However, the kernel of a convolutional layer is a 4D tensor of the shape of number input multiplied by width multiplied by the heights multiplied by the number of outputs. Um, in such a case, W is reshaped from the kernel to the shape number of inputs multiplied by the width, the height, and then multiplied by number of outputs. In simulated experiments on cipher data, the writers investigated the effect of structured and sketched update techniques uh, on the convergence of the federated averaging algorithm, with only a slight degrading in convergence speed. They were able to reduce the total amount of data communicated by 2 orders of magnitude. This let them obtain a good prediction accuracy with an all-convolutional model, while in total communicating less information than the size of the original cipher data. In larger realistic experiment on user partitioned text data, the writers show that they were able to efficiently train a recurrent neural network for next word prediction before even using the data of every user once. Finally, they noted that they achieved the best results, including the pre-processing of updates with structured random ratios. The first type of communication efficient update restricts the update's HIT to have a pre-specified structure. We're talking about the structure update now. Two types of structures are considered in the paper, the low rank and random mask. It is important to stress that the writers train directly the updates of the structure as opposed to approximating or sketching general updates with an object of a specific structure. The low rank. The writers enforce every update to local model HIT, which belongs to R of two dimensions, to be a low rank matrix of rank at most k, where k is a fixed number. In order to do so, they express HIT, which is the update, as the product of two matrices, AIT and BIT, where AIT belongs to R, the matrix D by K, and BIT belongs to RK by D2. In subsequent computation, they generated AIT randomly and considered a constant during a local training procedure, and they optimized only BIT. Note that in practical implementation, AIT can, in this case, be compressed in the form of a random seed, and the clients only need to send trained BIT to the server. Such approach immediately saves a factor of D1 over K in communication. They generated the matrix AIT afresh in each round and for each client independently. They also tried fixing BIT and training AIT as well as training both AIT and BIT. Neither performed as well. An intuitive explanation for this observation is the following. We can interpret BIT as a projection matrix and AIT as a reconstruction matrix. Fixing AIT and optimizing for BIT is akin to asking a given random reconstruction what is the projection that will recover most information. In this case, if the reconstruction is full rank, the projection that recovers space spanned by top k eigenvalue exists. However, if we randomly fix the projection and search for a reconstruction, we can be unlucky, and the important subspaces might have been projected out, meaning that there is no reconstruction that will do as well as possible or will be very hard to find. Random mask. The writers restrict the update HIT to be sparse matrix, following a predefined random sparsity pattern. The pattern is generated afresh in each round and for each client independently, similar to the low rank approach. The sparse pattern can be fully specified by a random seed, and therefore it is only required to send the values of the non-zeros entire of entries of HIT along with the seed. The second type of updates addressing communication cost first computes the full HIT during local training without any constraints, then approximate or encode the update in a lossy, compressed form before sending to the server. The server decodes the updates before doing the aggregation. The writers experiment with multiple tools in order to perform the sketching, which are mutually compatible and can be used jointly. Now, the subsampling, instead of sending HIT, each client only communicates matrix HIT bar, which is formed from a random subset of the scaled value of HIT. The server then averages the subsample updates, producing the global update HIT bar. This can be done so that the average of the sampled updates is an unbiased estimator of the true average. EHT equals to HT. Like the random mask structured update, the mask is randomized independently for each client in each round, and the mask itself can be stored as a synchronized seed. Probabilistic quantization. Another way of compressing the updates is by quantizing the weights. First, describe the algorithm of quantizing each scalar to one bit. Consider the update HIT. Let H equals to H, H1, H2, H3, etc. until HD by D2 equals the vector HIT. And let H max equals max J, Hj, and H minimum equals minimum J of Hj. The compressed update of H denoted by H bar is generated as follows. So using these equations, it is easy to show that H bar is an unbiased estimator of H. This method provides 32 multipliers of compression compared to a 4-byte float. One can also generalize the above to more than one bit for each scalar. For b-bit quantization, we first equally divide h minimum and h maximum into 2 to the power of b intervals. Suppose hi falls in the interval bounded by h prime and h double prime. The quantization operates by replacing h minimum and h maximum um, of the above equation by h prime and h double prime respectively. Parameter b then allows for simple way to balancing accuracy and communication cost. Another quantization approach also motivated by reduction of communication while averaging vectors. Incremental, randomized, and distributed optimizing algorithms can be similarly analyzed in quantized update settings. Improving the quantization by structured random rotations, the above one bit and multi-bit quantization approach work best when the scales are approximately equal across different dimensions. For example, when max equals 1 and minimum equals minus 1, and most of values are zeros, the 1-bit quantization will lead to a large error. We note that applying a random rotation on H before the quantization or multiplying H by random orthogonal matrix solves this issue. The structured random rotation can reduce the quantization error by a factor of O d over logarithm d, where d is the dimension of H. In the decoding phase, the server needs to perform the inverse rotation before aggregating all the updates. Note that in practice, the dimension of H can easily be as high as D equals to 106 or more, and it is computationally prohibitive to generate O d to the power 3 and apply O d to the power 2, a general rotation matrix. The writers use a type of structured rotation matrix which is the product of a Walsh-Hadamard matrix and a binary diagonal matrix. This reduces the computational complexity of generating and applying the matrix to OD and OD logarithm D, which is negligible compared to the local training within federated learning. The writers conducted experiments using federated learning to train deep neural networks for two different tasks. First, they experimented with the Cipher-10 image classification task with convolutional networks and artificially partitioned dataset and explored properties of their proposed algorithms in details. Second, they used more realistic scenario for federated learning, the public Reddit post data, to train a recurrent network for next word prediction. The Reddit dataset is particularly useful for simulated federal learning experiments as it comes with natural per user data partition. This includes many of the characteristics expected to arise in particular implementation. Now the experiments. For example, many users have relatively few data points and words used by most users and are clustered around a specific topic of interest of the particular user. We can see here that we have four graphs. Structured update with the cipher data for size reduction versus modes, and low rank update in the top row, the random mask update in the bottom row. And we can see the differences. Excuse me. In all their experiments, they employed the federated averaging algorithm, which significantly decreases the number of rounds of communication required to train a good model. Nevertheless, they expected their techniques would show a similar reduction in communication costs when applied to asynchronous distributed SGD. For federated averaging on each round, they selected multiple clients uniformly at random, each of which performed several epochs of SGD with a learning rate of mu on their local dataset. For the structured update, SGD is restricted to only update in the restricted space. This is only the entries of BIT for low rank updates and the unmasked entries for the random mask technique. From this updated model, they computed the updates for each layer HIT. In all cases, they ran the experiments with a range of choices of learning rate and reported the best results. The convolutional models on the Cipher-10 dataset. In this section, the writers used the Cipher-10 dataset to investigate the properties of their proposed methods as part of federated averaging algorithm. There are 50,000 training examples in the Cipher-10 dataset, which the writers randomly partitioned into 100 clients, each containing 500 training examples. The model architecture they used was the old convolutional model taken from what is described as Model C in Spring Imberg at 2014 for a total of over 106 parameters. While this model was not the state of the art, it was sufficient enough for their needs, as their goal was to evaluate their compression methods, not to achieve the best possible accuracy on this task. The model has 9 convolutional layers, first and last of which have significantly fewer parameters than the others. In this whole section, when they try to reduce the size, the individual updates, they only compress the inner 7 layers, each of which with the same parameter. They denote this by keyword mode for all approaches. For low rank updates, mode 25 mode equals 25% refers to the rank of the update being set to fourth of rank of, of the full layer transformation. For random mask or sketching, this refers to all but 25% of the parameters being zeroed out. In the first experiment, summarized in Figure 1, they compared the two types of structured updates introduced: low rank in the top row and the random mask in the bottom row. The main message was that random mask performs significantly better than low rank as we reduce the size of the updates. In particular, the convergence speed of random masks seems to be essentially unaffected when measured in terms of number of rounds. Consequently, if the goal was to only minimize the upload size, the version with the reduced update updated size is a clear winner. In Figure 2, this one, they compare the performance of structured and sketched updates without any quantization. Since in the above, the structured random mask updates performed better, they omit low rank update for clarity from this comparison. They compare this with the performance of the sketched updates um, with and without pre-processing the update using random rotation and for two different modes. They denote the randomized had more rotation by HD and no rotation by I. This is Figure 2. The intuitive expectation is that directly learning the structured random mask updates should be better than learning an unstructured update, which is then sketched to be represented with the same number of parameters. This is because by sketching we throw away some of the information obtained during training. The fact that with sketching the updates we should converge to a slightly lower accuracy can be theoretically supported using analogous argument. Since sketching the updates increases the variance directly appearing in convergence analysis. We see this behavior when using the structured random mask updates, we can eventually converge to slightly higher accuracy. However, we also see that with sketching the update, we are able to attain modest accuracy, 85%, slightly faster. In the last experiment on cipher data, the writers focused on interplay of all three elements: subsampling, quantization, and random rotations. Note that combination of all these tools will enable higher comparison rate than in the above experiments. Each pair of plots in figure 3, this one, focus on mode subsampling, and in each of them they plot performance with different bits used in quantization, with or without the random rotations. In all plots, the random rotation improves the performance. In general, the behavior of the algorithm is less stable without the rotation, particularly with the small number of quantization bits and smaller modes. In order to highlight the potential of communication savings, note that by pre-processing with random rotation, sketching out all but 6.25% elements of the update and using 2 bits for quantization, we get only a minor drop in conversions, while saving factor of 256 in terms of bits needed to be presented to represent the updates to individual layers. Finally, if we were interested in minimizing the amount of data uploaded, we can obtain a modest accuracy, say 85%, while in total communicating less than half of what we would be required to upload the original data. This is figure 3. It's a comparison of sketched updates, uh, combining pre-processing the updates with the rotations, quantization, and subsampling the cipher data. LSTM next word prediction on Reddit data. The writers constructed the dataset for simulating federated learning based on the data containing uh, publicly available post comments on Reddit. Critically, critically, each post in the database is keyed by an author, so the writers can group the data by these keys, assuming of one client device per author. Some authors have a very large number of posts, but in each round of federated averaging, they process at most 32,000 tokens per user. They omit authors with fewer than 1,600 tokens, since there's constant overhead per client, and the simulated end users with little data don't contribute much to training. This leaves a dataset of 763,430 users with an average of 24,791 tokens per user. For evaluation, the writers use a relatively small test set of 75,122 tokens formed from random held-out posts. Based on this data, the writers trained a LSTM next word prediction model. The model was trained to predict the next word given the current word and a start vector passed from the previous time step. The model works as follows. Word ST is mapped to an embedding vector ET, which is part of the R96, by looking up the word in a direct dictionary of 10,017 words. ET is then composed with the state emitted by the model in the previous time step ST1, which is part of R256, to emit a new state vector ST and an output embedding OT, which is part of R96. The output embedding is scored against the embedding of each item in the vocabulary via inner product before being normalized with softmax to compute a probability distribution over the vocabulary. Like other standard language models, we treat every input sequence as beginning with an implicit BOS, beginning of sequence, token, and ending with an implicit end of sequence token. Unlike standard LSTM language models, the writer's model uses the same learned embedding for both the uh, embedding and softmax layers. This reduces the size of the model by about 40% for a small decrease in model quality and advantages uh, trade-off for mobile applications. Another range from many structured LSTM, excuse me, another change from many standard LSTM recurrent neural networks approaches is that uh, the writers train these models to restrict the word embeddings to have a fixed L2 norm of 1, a modification found to improve convergence time. In total, the model has 1.35 million parameters. In order to reduce the size of the update, the writer sketched all the model variables except some small variables such as biases, which consume less than 0.01% of memory. They evaluate using accuracy top 1, the probability that the word to which the model assigns highest probability is correct. They always count it as a mistake if the true next word is not in the dictionary, even if the model predicts unknown. This is figure 4, comparison of sketched updates training a recurrent model of the Reddit data, randomly sampling 50 clients per round. In figure 4, the writers run a federated averaging algorithm on Reddit data with various parameters that specify the sketching. In every iteration, they randomly sample 50 users that compute update based on the data available locally, sketch it, and all the updates are averaged. Experiments with sampling 10, 20, and 100 clients in each round provided similar conclusions as the following. In all the plots, they combined the three components for sketching the updates. First, they apply a random rotation to pre-process the local update. Further sketch fraction set to either zero point 0.1 or 1 denotes fraction of the elements of the update being subsampled. Now they plot they plot this against the number of iteration of the algorithm. This is figure 5. The effect of pre-processing with the random rotation has significantly positive effect, practically, particularly with small number of quantization bits. For all choices of the subsampling ratio, randomized Hadamard transform with quantization into 2 bits doesn't incur uh, any loss in performance. An important measure to highlight is the number of rounds displayed in the plots is 2000. Since we sample 50 users per round, this experiment would not touch the data of most users even once. This further strengthens the claim that applying federated learning in realistic setting is possible without affecting the user experience in any way. They plot the same data against the total number of megabytes that would need to be communicated by clients back to the server. From these plots, if one needed to primarily minimize this metric, the techniques proposed are extremely efficient. Of course, neither of these objectives is what they would optimize for in a particular application. Nevertheless, given the current lack of experience with issues inherent in large-scale deployment of federated learning, they believe that these are useful proxies for what will be relevant in a particular application. Finally, in Figure 5 that we saw, um, they study the effect of number of clients they use in a single round on the convergence. They ran the federated averaging algorithm for a fixed number of round 500 to 2500 with varying number of clients per round. Quantize updates to 1 bit, and plot the resulting accuracy. They see that with enough clients per round, 1024 in this case, they can reduce the fraction of subsampling elements down to 1%, with only minor drop in accuracy compared to 10%. This suggests as an important and practical trade-off in the federated settings. One can select more clients in each round while having each of them communicate less and obtain the same accuracy as using fewer clients but having each of them communicate more. The, the former may be preferable when many clients are available but each has very limited upload bandwidth, which is sitting common in practice. The conclusion: one problem with the federated learning is the cost of the uploading data from clients. The suggested solutions are very effective, and the results from the experiments prove that point. The communication technologies in some countries are greatly different from what people are used to have in other countries. Someone would argue that the internet on their personal phone is fast enough to send any kind of updates to the servers, but this is not the general case. This paper helps people who live in remote areas with limited access to the internet, sending feedback and updates from their devices. We can see so many applications becoming part of our lives and using federated learning to get updates, such as Google Maps, for example. In many cases, these updates are essential for the quality of the product and could actually save lives. Sketch updates give more control over the packets and deliver better results. Thank you so much.